All right, inverse trigonometric antiderivatives. We've looked at how to find these derivatives. So derivative of inverse sine ends up being what we have here. Inverse cosine is the exact same integral, except that it comes out negative. Derivative of secant and secant, inverse cosecant, again, are the same, just separated by a negative sign. Same with tangent and cotangent, inverse of those, same, except again the negative being the difference. Some things to notice about these are some ones you would either have to like work out the derivative if you forgot on the test, or might be a good thing right before the test kind of go through and memorize these. But all of them, some similarities, they all have a 1 in there, is something to remember. All of them have a term squared in here, is something to remember. Not all of them, but a lot of them have the square root symbol in there. So if you see an antiderivative or integral where there's a square root with something squared in 1 in there, it might be a clue, except for the tangent and cotangent ones, they aren't square root there. But those are some similarities and some things, if you got to the test and you notice those, it would be the way to go. So let's try a few here. First one, evaluate this integral. So this one's a definite integral. We got some limits on there. We still need to know what's the antiderivative of what we got here. One thing to notice, if you would try like some substitution, if that was your first thought, not going to work on this one because we don't have a way of getting rid of that extra 2x there. So if you try substitution, you know it doesn't work, that might be a good clue. This is one of those inverse trig ones. So this was the inverse trig of tangent. So that's our antiderivative here, inverse tangent, evaluated at both 1 and -1. So now what we want to do, figure out what's the inverse tangent of 1 minus the inverse tangent at -1. Those we could evaluate with calculator by doing second tan and then putting in either 1 or -1, and you get about 0.785. If you do the -1, I believe you get the same thing but negative. And then adding those together comes out to be about 1.571. One thing to note about that, if it were to be like a multiple choice question and you got some options up here, maybe your options were like 0, pi over 2, negative pi over 2, pi over 4, something like that. If those are your answers, you should be able to match this one up. This one actually does come out to be pi over 2. This is the approximation here for pi over 2. Reason being, if we're doing inverse tangent, if you think through unit circle here, remember you have an ordered pair that gives you a cosine value and then a sine value. So if the inverse tangent is 1, that means the two, because tangent's equal to sine over cosine, and we get 1, that means the sine and cosine values must be the same in order to give us a value of 1. Well, that would happen at a 45-degree angle, or 45 degrees is the same as pi over 4. And so that's why this and this are the approximations of pi over 4. That's why when we end up putting these together, because we end up changing this to adding here, this would be pi over 2. All right, let's have you guys try this one. So pause it and see what you get on this. All right, let's see if when you were doing this one, you should have noticed this one is the same here as our inverse cosine one. So antiderivative here is cosine inverse. One other thing with this one, if you were thrown off by this, remember we can always move that down, so then you can see it a little better that it is that inverse cosine one. So if they put the dx on top, it just means there's a 1 there. So this one, like we said, is inverse cosine evaluated at both 1 and 0. So you got to figure out what's inverse cosine of 1 minus cosine inverse of 0. The place on the unit circle where if you did cosine you would get 1 would be at 0 radians, because that would be place where your cosine value is 1 is right there. Cosine's your x value, so that would be at 0 degrees. That's right on the line. The place where it would equal 0, that would be here, because that's 0 now is your first one, so that would be at 90 degrees, or that's the same as pi over 2. And so the answer on this one comes out to be negative pi over 2. All right, let's look at some indefinite ones. So now we don't have any more limits on there. Find the antiderivative of this. So this one definitely looks like one of those inverse trig ones. But remember that in the inverse trig ones, you didn't normally have numbers here. So what we got to figure out on ones like this is what's being squared there, because we need this as a value squared minus 1. And so looks like here, definitely there's an x being squared. The number being squared here would be 4. And so this one has kind of a function in a function. This would be one we'd want to try some substitution on. So let's substitute u for 4x. That way it'll end up looking like one of our inverse trig ones there. So now we got to take the derivative of both sides. I'm going to, I forgot my dx in here. I don't see another 4 to cancel out there, so I'm going to move that to the other side to do our replacement here. So our dx is going to turn into 1/4 du. Substituting in our other stuff, we got 1 over, this will turn into u squared minus 1. We do have this x, though, that we need to replace as well. So we got to figure out what would x be equivalent to here. Well, just doing some dividing there, we see that x would be equal to u over 4. Or another way of writing that would be 1/4 u. So if we replace that as well, that's our new integral. There's a 1/4 here outside the fraction and 1 in the denominator, so those should cancel out. And so now we just have the integral of this, and now this should look like one of those we had on our sheet. That one is inverse secant, I believe. Let's see. Yes, that one looks like our inverse secant one. So now we can do that antiderivative. It's inverse secant of u plus a possible constant. Remember on these substitution ones, though, our last step now, we need to substitute our value of u back in to get our final answer. So final answer would be inverse secant of 4x plus c. All right, why don't you pause again and try one out and see what you get on this one. All right, let's see how you did here. Again, we want to figure out in this denominator what is being squared here, because all these inverse trig ones have something squared there. So it looks like it'd be x cubed being squared. So off on the side, you want to do that substitution. Derivative of both sides would be this. On this one, we got 3x squared dx right here, so that should all turn into our du. and then this would turn into our u. So now our integral becomes 1 over square root 1 minus u squared du. And that one is the inverse sine. And, whoop, that's again sine antiderivative here. Said it, but wrote it wrong. Inverse sine of u plus c. And then last step, make sure you did substitute back in, so the answer would be inverse sine of x cubed plus c. All right, hopefully you got that one. All right, last one here. Looking at another one, again, looks like kind of one of those inverse trig ones a little bit here. You got to, again, find something that is going to be squared for this, but also now we got this 25. All those other ones, remember, we got 1 there. So what you have to do is if you don't have a 1 in the denominator, you first have to factor that number out. So what I'm going to do here is I'm going to factor out a 25. So if I do that, this would be 1 now plus e to the 6x over 25. And now we got that 1 that all those inverse trig derivatives have. So next, I'm going to take this constant. Let's pull that out. It's in the denominator, so it'd be like a 1 over 25 that we'd be pulling out. Now let's figure out what's being squared here, because all those inverse trig ones have something squared. So on the bottom, we know it'd be 5, because 5 squared is 25. On top, if we do something here, it's got to have e and it's going to be squared. We want the two exponents here to end up equaling e to the 6x. And remember, when you do power to power, you multiply, so that must be 3x. So this is going to be e to the 3x being squared. So now that we know what's being squared there, that would become our substitution. So we want to substitute e to the 3x over 5. Finding our derivative, now, whoop, sorry, this should be du. This would be doing a derivative with chain rule. So derivative of the outside would be the same thing, times derivative of the inside, derivative of 3x would be a 3, so we get like 3/5 e to the 3x. I don't see a 3/5 to cancel out there, so let's multiply by the reciprocal, get to that to the other side. So 3/5 du would be equal to e to the 3x. Oh, and I forgot my dx on here. All right, so looks like this right here would turn into our 5/3 du, and then we got our substitution for u here. So making both of those. We got this, all that stuff I got circled turns into 5/3 du. I'm going to put the 5/3 out in front of our integral. So now this is just 1 over, and we got du as our variable of integration. And then on the bottom, we'd have 1 plus u squared. That took a little work, but now that definitely looks like our inverse trig antiderivative. And so what we got here is, inverse tangent for our anti-trig derivative. So this is inverse tangent of u. Also, we got this constant over here. It looks like 5 goes in here 5 times. So on top, we'd have a 1 over 15. And then plus some possible constants. So final answer, 1 over 15 times the inverse tangent. Make our substitution back in here. So e to the 3x over 5 plus c. That one a little bit harder because you had to do some dividing. So if there's ever a number other than 1 here, factor it out first to make it 1 and then figure out what's being squared.